Thank you so much, Deb. And it's a real pleasure to be here. And on behalf of the OLI team, we really appreciate NAWI's inviting us to make this presentation. And thanks to everybody for attending this presentation. So if you can go to the next slide, please, Andre. A quick view of the agenda. I'll give a quick overview of OLI Systems, and then we'll have Dr. Andrea and Darko talk to us about the fundamentals of our thermodynamic models. And then we'll have Dr. AJ Gerbino and Kristen Jenkins talk to you about some very specific use case and application examples for industrial water wastewater treatment. And then finally, we'll summarize our collaboration with NAWI in 2 specific areas, and then open up for Q&A, and hopefully we have some time for that. Next slide, please, Andre. Yeah, one more. So really, electrolytes and water chemistry influence a lot of key reactions and phenomena. When you look at industrial chemical processes, whether they be oil and gas, chemicals, metals, mining, power generation, a lot of these are critical. For example, oxidation, reduction, neutralization, pH control, mineral scaling, corrosion, all of these sort of phenomena and reactions, they impact how assets and equipment are designed, how processes are designed, and eventually how they optimize across the life cycle. So essentially, that's sort of the quest for OLI. We really look to see how we can leverage the fundamental understanding of these reactions and phenomena to ultimately help to improve these processes and help to maximize profitability and deliver greater productivity as well as increase sustainability. Next slide, please. So specifically today, we're talking about industrial water, wastewater treatment, and a quick summary of this is sort of the theme that you'll hear ongoing in the presentation today. But clearly, from a scope perspective, OLI brings deep chemistry expertise into various source waters here. You can see on the left in the water wastewater treatment area. We do a lot in terms of the treatment for discharge, brine valorization, and a wide range of sort of produced water source waters as well as seawater desalination. And the kind of capabilities we provide from a modeling perspective, it spans thermophysical properties, transport properties, actually predicting scaling and also predicting inhibition and anti-scaling behavior, general and localized corrosion, evaporation crystallization, surface complexation, reverse osmosis, ZLD, and quite a few other capabilities. So that's kind of a quick overview for you there. Next slide, please. So really, OLI, if you look at our evolution, we're a small company, a little bit over 40 employees, but we've been around for the last 5 decades, and we bring a lot of deep expertise in electrolyte and water chemistry. So it starts with a very rich software portfolio, which is powered by a vast database of properties that spans 80 elements of the periodic table and over 6,000 species, and a software and consulting services capabilities. A strong commitment to R&D. We've done a lot of work over the years, and our platform represents a $150 million investment over the years and covers thousands of applications. We have rich expertise and resources. Some of the experts in this area globally. Lots of work in industry standards bodies and application expertise in industrial markets, as well as consulting experience is what we bring to the table here. And finally, we do have a global footprint. We are in 35 different countries, over 500 different clients, have won awards and recognition from an R&D perspective as well, and have a good channel partner ecosystem as well for commercializing software technology. Next slide, please. A quick view. So across all these verticals, we do support some of the largest operators, consultant companies in the world in these areas, whether it be oil and gas, chemicals, mining, metals, etc. Clearly, water treatment is sort of a horizontal that cuts across these, but I've shown this as a vertical here. We do have partnerships with some of the leading software players in the process simulation space, and clearly now we're very excited to be working with NAWI as well in the water treatment area. And that's kind of a quick view that we do keep company with a strong ecosystem of partners in trying to commercialize what we do and deliver real world applications using all the science and the technology. Next slide, please. So this is just to kind of communicate that over the last 5 decades, we have a very rich history of collaborating with various government organizations, research and development arms of commercial companies and academic groups extensively in various areas. So whether it be Critical Materials Institute for some of the critical materials that we're working with, some of the carbon capture work we're doing with the Department of Energy funded projects, clearly now working with NAWI is really an exciting piece for us to add to what we've been doing. And we do this in a wide range of sponsored research programs. So these are collaborations to develop new chemistry, new thermodynamic models, and validate the models. We also do custom kinds of JIPs, which we have led with many of the large operators in the oil and gas and related industries, chemicals as well in the past. And extensively work with academic partners as well. So really working with an organization like NAWI feels like second nature to us, and we're really excited to extend this collaboration. And we really bring a lot of experience working with Department of Energy in a wide range of areas through the national labs and other funded sources. Next slide, please, Andre. So this is a view of our sort of solutions capability. We have a rich capability set, which starts in the bottom. You can see the property database. So this is sort of the crown jewels of what OLI has developed over 5 decades. And the fundamental thermodynamic models is that sort of next layer there you see in the slide from the bottom. And when you combine these two, what we have is the OLI engine. That's the computational engine that leverages all the numerical algorithms that correspond to these thermodynamic models. And then we have software capabilities that are built on top of this layer. So essentially, we have a Windows-based software platform for analyzing things like just the chemical streams, understanding chemistry behavior, also predicting phenomena like mineral scaling, as well as corrosion. We also do like mass energy balance with flow sheets to understand actually a full process simulation. And then we also have the capability to integrate our chemistry model into third-party commercial simulators. And whether it be an Aspen or Aviva products like Pro2 and so on, you'll see a range of products that we actually integrate into. And we also provide a Windows-based API for software development based on the OLI engine. And then more recently, we've been excited to bring to market our cloud platform. So we actually now have cloud APIs with RESTful technology, which is really sort of the state of the art, along with something called an application builder, which actually allows the ability to leverage the OLI capability to actually publish cloud applications on the fly. So essentially, that's sort of our software portfolio. We also have strong technical support capabilities, education, training, as well as consulting services, where we bring a lot of our industry-specific application knowledge and expertise across these different vertical industries that we've talked about before, specifically focusing on industrial chemical processes, as well as working with academia and research government organizations. Next slide, please, Andre. So this is a quick view for you of our key applications. Clearly we work in a broad range of industrial sort of applications. The water treatment today is clearly the focus, but I just wanted to make sure that you understand the breadth in these verticals, because water treatment is really a horizontal. So we bring in a lot of that expertise, understanding, vertical domain expertise in these other industries, in addition to doing water, wastewater treatment in a more comprehensive way. So just like we saw earlier on the second slide that I shared, you can see some of the key applications in water treatment, but it also goes to the areas like downstream applications where things like sour gas or flue gas desulfurization, to the chemical industry, to mining metals and extracting lithium and rare earths, as well as power generation and some energy storage in terms of battery recycling work we're doing as well. So clearly, just a broad range of capabilities, leveraging the electrolyte technology that OLI brings to the table. Next slide, please, Andre. So this is a summary of our unique and differentiated chemistries. So this is very unique to OLI and represents what we've done over the last 5 decades over many different projects. So just a sampling of the key chemistries that we bring. So clearly on the right-hand side, you can see the water treatment area, where a lot of these pollutants, just a few of them are listed here. And then things like surface complexation with other capabilities on the chemistry side. And then you can also see the traditional areas for oil and gas, refining, metals, mining, as well as a lot of alloys that we've also been able to characterize. Right, you can see in the bottom of the slide here. And the heart of this is around mineral scale prediction, as well as scale inhibition and corrosion mitigation. Great. Next slide, please, Andrew. Excellent. So I'll turn back to you, Andre. Thank you.
Thank you, Vinny. Now we are going to talk about the fundamentals of our prediction technology. At the very core of our software products and our methodology lies a thermodynamic model. It's a thermodynamic model and a thermophysical property model that allows us to predict the physical properties of aqueous systems, electrolyte systems, and in a very wide range of temperatures, compositions, pressures. This is a speciation-based model. It means that we endeavor to account for the speciation as accurately as possible to reproduce the properties of aqueous systems. Since it's a speciation-based model, we can model reaction equilibria between various species in the solution, and those reaction equilibria include acid-base, complexation reactions, redox reactions. Solid phase precipitation is also a form of reaction equilibria between solid phases and aqueous species. And also we model surface complexation and other adsorption phenomena like ion exchange or molecular adsorption. This diagram here on the right-hand side illustrates the conceptual structure of our thermophysical property model. Since this is a speciation-based model, we pay particular attention to the standard state properties of species, which describe the behavior of species at infinite dilution in water and their interactions with water. Then we have an excess Gibbs energy model, which takes us from the infinite dilution limit to concentrated systems, and in some cases going all the way to fused salts and definitely to solid liquid saturation. Then for the gas phase, we use an equation of state. Then this framework is supported by a large database of the thermochemistry of the species, solid, gaseous, aqueous species. Also, we include the adsorption models, surface complexation, ion exchange, and molecular adsorption. This is all put together into a thermodynamic framework, and then this thermodynamic framework feeds into an algorithm for calculating phase and chemical equilibria, which give us a very comprehensive treatment of systems that may contain a gas phase, a water-rich liquid phase, possibly water-depleted or non-aqueous liquid phases, such as those that are relevant in extraction phenomena, and multiple solid phases. Now, this is also supported by models for transport properties, including electrical conductivity, viscosity, thermal conductivity, and also self-diffusivity, and also surface tension and interfacial tension. A few words about how the thermodynamic model is structured. The standard state properties are the starting point for our calculations, and for this purpose, we use the Helgeson-Kirkham-Flowers equation for ionic and neutral species. This is basically a model that takes into account the electrostatic interactions, the solvation of an ion in a dielectric continuum, and also the specific interactions between an ion and the solvation layer around. Then for the excess Gibbs energy, we use a formulation that incorporates three contributions. The first contribution accounts for the long-range interactions from the Pitzer-de-Bihicle model, which is basically interactions in a dielectric continuum. And then we have a local composition term for interactions between neutral molecules, and the term that is most important for aqueous species, that is the ion interaction term, which is conceptually constructed using a virial expansion with an ionic strength-dependent second virial coefficient. And this is, of course, supported by a very extensive database of interaction parameters and standard state parameters. So now I'm going to give you a short overview of what we can do with the model and how the properties that we are generating can be useful for aqueous systems and especially for water treatment applications. The first property that I would like to highlight is water activity, which is a simple consequence of the excess Gibbs energy model. Water activity is, of course, necessary for predicting osmotic pressure, boiling point elevation, and essentially all vapor-liquid related phenomena, including thermal separation processes. It's been validated against experimental data for both simple and complex systems. And this is an example. In this diagram, we plot water activity as a function of the salt fraction. And this is just for simple systems like sodium chloride or calcium chloride or lithium chloride or some nitrates. This is the pattern of water activity, and then it transitions to a flat region when we reach solid saturation at the point that is indicated by the arrow. And of course, this is the high accuracy of this property is necessary to predict osmotic pressure with high accuracy. Now, we have validated such predictions not just for simple systems, but also for multi-component solutions, as shown here in this diagram for water activity against the salt mole fractions for various mixtures of chlorides and nitrates. And we can see that the plot has multiple breakpoints, which corresponds to the appearance of one phase. As we increase the concentration, then we have a liquid solution in the presence of one liquid phase, and then another liquid phase appears, and then it goes flat because the number of degrees of freedom is reduced. So this is the kind of simulations that we can easily make using the model. Now, solid-liquid equilibrium. That is essential because the world of electrolytes involves the presence of multiple possible solid phases, and those solid phases may be quite complex. Those may be simple salts, those may be hydrated salts, they can be double salts, and in some cases even triple salts. So we can predict such phenomena, solubility phenomena, going essentially from infinite dilution in water to all the way to solid saturation and even fused salts. And here these diagrams are just simple illustrations of how it works. For example, here calcium chloride, solubility as a function of temperature. This blue branch is the solubility of ice. It starts at 0 degrees. Now we have a eutectic point, and then we have multiple hydrated phases that change, and then we go up to 300 degrees C, where the solubility is about 88%. So we don't have any concentration limits in this model. And now moving on to ternary systems, this is a plot for a relatively simple ternary system where we have sodium chloride and sodium nitrate. Here is sodium chloride on the vertical axis, sodium nitrate on the horizontal axis, and we have the solubilities of the phases that coexist with the aqueous phase. What is important is that this is not simple curve fit. This is a simultaneous representation of multiple physical phenomena. So for example, here we have the solubility in the mixtures of sodium chloride and nitrate. And here at the same time, we calculate the water activity from the same model along the saturation for the same mixture. And you can easily map this water activity as a function of the sodium nitrate fraction, which corresponds to going along one of these branches of the solubility curve. So in this way, we know the conditions at which we have solid precipitation. We know immediately, for example, whether the vapor pressure is, what the osmotic pressure is going to be. Now, scaling. Mineral scaling, that is extremely important in many separation processes, whether it's thermal separation processes, or whether it's scaling in natural systems, or whether it's scaling on membrane surfaces. We have put a lot of effort into creating a comprehensive database for various mineral scales. The approach that we took is that we looked at essentially all available ternary, binary and ternary combinations of key cations, like sodium, potassium, magnesium, calcium, strontium, barium, iron, zinc, lead, aluminum, etc., and key anions like chlorides, sulfates, carbonates, sulfides, silicates. And then we analyzed those binary and ternary combinations. We developed thermodynamic parameters. We developed thermochemical properties for various anhydrous and hydrated salts. And we have analyzed both stable and metastable species. And here is a simple example for calcium sulfate, one of the important mineral scales in practical applications. This is the solubility of calcium sulfate as a function of temperature. And calcium sulfate forms three important solid phases, which is gypsum, anhydrite. Oh, there's a mistake. This should be gypsum. Anhydrite and hemihydrate. And under some conditions, they can be stable or metastable. The main advantage of the ionic-based model is that we can model the effect of salinity and the presence of complicated aqueous systems on the solubility. And sometimes the solubility is quite strongly dependent on the presence of other species. This is an example for calcium sulfate. Again, the same calcium sulfate in sodium chloride solutions, solubility of sodium sulfate as a function of sodium chloride. Now, there is no common ion effect, but there is a strong ion interaction effect. And this changes the solubility of gypsum, in this case at room temperature. The purple curves are at room temperature. And then at high temperatures like 150 and 200, the solubility increases. It shows a different pattern because this depends not just on temperature, but also on the presence, the activities of the other ions in the solution. One thing that I want to highlight is that the stability versus metastability of the solid species changes. Like in this example, at 25 degrees at low salinity, gypsum is stable. Then at higher salinities, anhydrite becomes stable, as shown here by this dashed curve, because this lower curve corresponds to the stable phase. And that is because the activity changes and water activity can be predicted by the model. So another example that I would like to highlight is the phase behavior and also speciation behavior of silica and silicates, which is very important in water treatment. So silicate thermodynamics is obviously very complex, and it needs to account for metastability, and it needs to account for speciation for various silicate species, various hydrolyzed forms, and various complexes. And here on the left-hand side, I'm just showing an illustration of an analysis that we have made for mixtures of calcium and silica. And here we especially paid attention to the solubility of the end members, meaning calcium hydroxide and amorphous silica, and the various calcium silicate phases. Now, question that we are facing in the analysis of process data and simulation of processes is very often what phases form in the timescale of hours, which very often corresponds to the operation of an industrial process, and then what phases will form as a result of aging. And the phase diagrams that we have constructed, like this one, can help us rationalize the solubility behavior of the metastable phases that form on a short time scale, and then the ones that form as a result of aging. So this diagram shows the behavior of calcium sulfate as an example, as a function of silica concentration on the vertical axis and calcium hydroxide concentration on horizontal axis. Here we have the calcium hydroxide solubility as the endpoint, amorphous silica solubility as the endpoint, and here we have the amorphous to bermorite and FWLI phases that are the first typically to form, and then upon aging they can transform into more stable phases, which are shown here by these blue and green symbols and calculated lines. So in all our thermodynamic analysis, we strive to match the reality, match the solubilities to the extent that we can, to the extent that the data are mutually consistent. Now, the last example from the thermodynamic part of our presentation is I want to show you a simulation of an experiment. The experiment is pretty simple. Calcium hydroxide is added stepwise to artificial geothermal water. And then the question is, what will be the evolution of dissolved silica? Because that is the objective of adding calcium hydroxide, is to lower the concentration of silica, for example, for boiler water applications. Here we assume that since this is a process happening on a relatively short time scale, then the amorphous calcium silicates will precipitate first and magnesium silicates will precipitate slowly. So here in this diagram on the left-hand side, we have the dissolved concentration of silica in the geothermal water. First it's flat and then it drops down. It doesn't go smoothly, and I will show in a second why. And then it goes down. At the same time, the dissolved calcium concentration first is slow and then it jumps in 2 stages. And then the pH evolution is also predicted together with the concentrations of silica and calcium. And here, this diagram explains what is happening, because the model can explain what is really happening when we add the calcium. So what happens first is the precipitation of calcium carbonate, and this accounts for the fact that first the silica doesn't budge, and then we have the precipitation of amorphous to bermorite and amorphous FWLI, and that accounts for the ultimate decrease in the solubility of in the amount of dissolved silica. So this is just a simple example how an experiment can be simulated and how we can match the experimental behavior. So with this, and I'm just going to summarize briefly the thermodynamic state of the art currently. Our mixed solvent electrolyte model can be used as an accurate tool to predict the properties of complex and multi-component systems, and that includes solubilities, including various competing stable and metastable phases, and that also includes speciation and reactions in aqueous systems. It includes vapor-liquid equilibria, it includes scaling tendencies, and as we will mention a little later in the context of kinetics, and many other properties. And the model is implemented in the OLI software. And now I'm going to turn it over to Kristen, who will talk about how the OLI software is actually used in practical applications. Kristen.
Thanks, Andre. I am the VP of Sustainability Solutions for OLI. I joined at the beginning of August and have a background in industrial water. I've been using the software for probably 15 years or so, and have developed some expertise in its use for industrial water. So I'm excited to be here and excited to see some familiar names on the attendee list. Next slide, thanks. The case study that we'll cover is related to silica scaling as well as some other minerals. It's a former manufacturing site that has the manufacturing buildings have been removed, but there's groundwater, contaminated groundwater below the site that's being recovered and discharged to a city publicly owned treatment works. So there's a groundwater collection system with a pump that then transfers the water through about a 2,000-foot pipeline that has developed significant scale over time. Acid cleaning of that line has been done periodically in the past, but more recently it's become less effective. And so the problem was to identify a solution to reduce scale buildup in the line, increase times between cleanings, and then also increase the life of the pump. So the pump was also getting scaled up and then also having to work at a relatively high pressure and was burning out fairly quickly. So to start the analysis, we had the following data available. We had cations, including the full suite of metals, and major cations like calcium, magnesium, sodium, potassium. We also had silica. For the anions, we only had chloride and sulfate. And then we also had pH, alkalinity, and then a elemental analysis of a part of the solid or scale material that was collected. And this is generally the kind of the minimum amount of data that you would need to run an analysis. However, you can fill in some missing data. So we went ahead and looked at it with the limited anion data. And, as Andre mentioned, those two anions are key in evaluating mineral scaling. So we'll get into the analysis on the next slide. So the first step is to reconcile the cations and anions. So this is a good best practice because many times there can be anomalies in analytical data. There can be missing data like what we had in this case. And so what we found and what's shown in the upper right screenshot is that the cation charge is less than the anion charge by about 0.02 equivalents per liter. So this tells us that the cations are low, and with the software, you can select which cation you want to balance it with, and can also look at different scenarios. And so in this case, we used the scale, the elemental analysis to support this because we knew we had a significant amount of calcium scale, and our starting calcium concentration was only 31 milligram per liter, which is shown in that lower right screenshot. And so when we balanced with calcium, then the amount of scale formed was fairly consistent with the elemental analysis of the scale. So we decided to move forward with the modeling as is. Another option would be to get more data, but we felt comfortable moving forward as is. Next slide. So as I mentioned, we compared the model predicted solids formed to what we saw on the analytical results, and it was very consistent. As shown in the last column on the screenshot to the right, the amorphous silica scale was almost 2,000 milligram per liter, and the calcium carbonate scale was around 900 milligram per liter. So we also did a laboratory acid wash of the solids and analyzed the material that remained, and that was only silica solids that remained. And so that's also consistent with calcium carbonate scale, since that can be dissolved. The software can also predict the quantity of scale formed. So, with the combination of the solid concentration and the flow rate, we were predicting about 143 pounds per day of calcite formed, and then 330 pounds per day of amorphous silica, which is, fairly significant. And then I'll point out there were two other minerals that were formed, but the concentrations were relatively low. And we're also predominantly silica and calcium based. So we really just focused on the amorphous silica and the calcium carbonate scale. Next slide. Another calculation that you can do in the software, and I should mention this is the OLI Studio stream analyzer software that was used for this analysis. You can do a survey calculation in very many different variables. In this case, we looked at the change in pH on scale formation, because many times changing the pH can change which minerals will form. And in this case, the raw water pH was around 11 to 11.5. The pH limit in the discharge to the city needed to be below 10.5. And so the site was lowering the pH on site prior to the transfer pump, and then discharged through that 2,000-foot line and then to the city manhole. And so what the survey calculation shows is that at the raw water pH of 11 to 11.5, you see some calcium scale, which is the light blue line, but you don't see any silica. The silica scale is the reddish line. And so as the pH is lowered down to 10.5 or below, usually it would be in the range of 10 to 10.5, the silica scale starts increasing. So one thought was, could we move the pH adjustment point to the end of the pipeline right before the manhole to the city, which would eliminate scaling in the on-site pipeline, but then that manhole was dedicated just to this site. So there were no other streams to offer dilution. So it would really just move the scaling issue to the city's piping. So we didn't want to do that. So we looked at other solutions. I should also mention too, I looked at how much scale is formed at the different pHs, and you can see it's fairly significant. The quantity of scale at a pH of 10 is 460 pounds per day, whereas at a pH of 12, it was 190. So, less than half the amount. So that, would have helped significantly in the amount of scale formed. And then if it was only calcium scale, then the acid cleanings would be a lot more effective. Next slide. And so we also, because of this, we hadn't found a viable solution yet. We wanted to look at treatment. And I'm going to turn it over to my colleague, AJ Gerbino, at this point to cover the treatment and that evaluation that was done in the flow sheet tool.
Thanks, Kristen. Yeah, so in this particular example, what we've done is to look to see, well, is there a process that you could use in order to remove the silicates, the silica from solution? And we came up with a hypothetical. What if we treated it like almost like a boiler feed water process, where you're adding magnesium to the system to absorb silica, or even precipitate silica onto with magnesium, and then remove the solids that way, or the silica that way. Also, since there was a little bit of arsenic in the sample, I thought it might be fun to include a little bit of hydrospheric oxide and show how that could be absorbed as well. And since we were already adding hydrospheric oxide, I took the technical license of adding a little bit of mercury to the system so we could remove that as well. So in this next slide, please. So just like Kristen talked about, the first thing you do is enter the experimental data into the software to create an electronic representation of it. In this case, we did a little differently. Kristen had already determined what the true calcium concentration could be. And I thought in this case, what we could do is just enter the silica as SiO2, since largely that's how it's provided by the lab. And then, as Kristen was describing, we can use the charge balance to determine how much hydroxide would be required to turn it into a silicate ion. So in this case, we are able to, in this approach, we're able to use the data as measured, and then use the software to determine the charge balance, and also at the same time the right pH. The next slide, please. I keep on pressing the down arrow and nothing happens. The next slide is the actual process we looked at. Very simple. It's actually two steps. You've got the first step where hydrospheric oxide is produced by adding ferric chloride to solution. The next step is where brucite, or hydrous magnesium oxide, is produced in order to absorb the silica. Each of them contain 4 steps. It has a heat exchanger, a chemical reactor, a settler, and then a filter. And the idea here is that you add sufficient amount of ferric chloride so that the concentration of arsenic and mercury reached a certain concentration. And then likewise with the MagOx, you add sufficient amount of magnesium oxide until you got your silica concentration down to a certain value. Now, generally you'd include a pH control on this, but since the pH was about 9.5 already, which is decent for the magnesium system, we left it alone and didn't touch the pH. Next slide, please. So real quickly, we have what are called controllers in order to determine the amount of material required or chemicals required. The first one, for example, is controlling the amount of ferric chloride required to set the arsenic plus mercury concentration at about 1 microgram per liter. And then to set this in the same way, we have a controller which adjusts the magnesium oxide input so that the dissolved silica concentration is about 26 milligrams per liter as silica. Next slide, please. So when you look at the results, you'll see the tables on the right-hand side. The left-hand side with some text just reflects some of the information that's described there. If you go from left to right with the tables, you can see about 30 kilograms of ferric chloride was required per day. You can see how much heat was required to raise the temperature to 25 degrees C from, I believe it was 15 C as the surface water starting point. And then the upper part where it says waste stream, that was the original composition that you see in the original water analysis. Below that, you have on the dry toxic solids that show, for example, the HFO, hydrospheric oxide, and all the different surface complexes that could form. You can see, for example, there are several species of arsenate that forms. There's even a couple of sulfate surfaces that can form as well. Further to the right, you have the amount of magnesium oxide required, about 300 kg per day. And since we're raising the temperature to about 90 degrees Celsius to take advantage of the low solubility of magnesium hydroxide at that temperature, you can see quite a bit of heat was required. But as a result, you're able to get the silica down to about 26 milligrams per liter. That's the third row where it says clarified liquid. And then at the bottom where it says dry sludge, you can see the various surface complexes that could form. Okay, and then the left side is just a little summary text that describes what I just described there. Okay, next slide, Andre. Good, so Kristen, I'll hand this back to you for the conclusion.
Okay, thanks, AJ. So what we found is that adsorption on reactive surfaces was successful to remove arsenic, mercury, as well as silica. We do see some competitive absorption in the amount of chemical needed, and the amount of reagent or magnesium oxide required was fairly significant at 300 kilograms per day. And then a significant amount of sludge was produced as well, 760 kilograms per day. And so because of this fairly onerous treatment approach, we decided to look at anti-scalant addition as a feasible approach. So anti-scalants were identified that are known to be successful for both calcite and amorphous silica formation. And we relied on a chemical vendor to provide a recommendation on the anti-scalant as well as the dosage. And so that leads to a feature that is being developed for OLI in terms of modeling scale formation and anti-scalants. Next slide. So what we'll be able to do in the software is look at the effect of different variables on the induction time or the time that it takes a scaling solid to form. So there's some correlation shown here in terms of how the background electrolyte can affect the induction time, and then we'll be able to model different anti-scalants and how those affect the induction time, and then also look at combination of these variables. And so at this point, I'll turn it back over to Andre, who will talk about our collaboration with NAWI.
Thank you, Kristen. Kristen's last slide was a segue to what we are going to do in the near future in collaboration with NAWI. The focus of one of our projects, which we are really excited about, is the kinetic modeling of scale formation and mineralization in brine solutions with and without scale inhibitors, especially high salinity brines. So the objective of this project is to develop an accurate model that predicts the type and the kinetics of mineral scale formation in the presence or absence of scale inhibitors and on surfaces, especially here we are focusing on membrane surfaces. This project is going to be performed as a collaborative project between SLAC National Accelerator Laboratory, National Energy Technology Laboratory, OLI, and Veolia. So what's the approach? The approach is to look very carefully at the experimental characteristics of mineral scale formation by measuring the silica and calcium, barium, and strontium sulfate induction times for a range of brine chemistries at various salinities and various temperatures using aqueous measurements, dynamic light scattering, and synchrotron X-ray scattering. Then another part of the project will be to characterize the silica phases formed in the presence of magnesium, calcium, aluminum, and iron, using synchrotron scattering and spectroscopy with sub-angstrom resolution. Those two tasks will be performed by SLAC. And the second task points out to the importance of characterizing what really forms in the when silica scaling is happening, what phases really form and how fast. And then we are going to use this information to parameterize our thermodynamic and kinetic model. For the calcium, barium, and sulfate and strontium sulfates, the model is pretty much well established. But for silica formation, there is still work that remains to be done. And there's, of course, a huge amount of work to be done to develop the kinetic induction time model. And finally, the model will be validated experimentally in laboratory-based RO and OARO reactors, followed by 2D and 3D micro and nanometer resolution chemical imaging that will be done at NETL. And Veolia will be our industrial advisor and will guide our selection of conditions and our experimentation. So this is what we are currently developing. We are currently developing a model for the kinetics of scale formation. It's still not in our software, but now it's very much in progress. The objective is to predict the crystallization induction time, which is the sum of the times for critical nucleus formation and the growth to a detectable size. So the concept is that the MSC thermodynamic model, which I showed you before, will provide the speciation, which is very important because we need to know what complexes, what species we have in the system, and it will predict the saturation index. Now, the saturation index is used as input to the classical nucleation theory, which provides a relationship between the saturation index and the induction time. And the classical nucleation theory is based on continuum thermodynamic treatment of clusters by imposing the capillarity approximation. What we can obtain is illustrated in this example, in this diagram. The log induction time is a function of the log of scaling saturation index to the power -2, and we can typically reproduce this kind of behavior, which often shows different patterns in the homogeneous and heterogeneous nucleation regime. So the importance of reliable kinetic data cannot be overestimated here because we really need very high quality data to rationalize the trends in experimental data. Currently the data in the literature are often sparse and scattered. So the new experimental data that will be generated at SLAC will be essential to create an accurate model. And the conceptual scheme of the work is shown here in this diagram with these three plots here. That first, the MSC will give us the solubility prediction, which we can do right now, although it will be fine-tuned for silicates. Then on top of it, we will implement the classical nucleation theory with appropriate parameterization to calculate the induction time. And here we already have some examples, for example, for barium sulfate, for the induction time as a function of the scaling index. And you can see that here in the two regimes, which are shown by the solid lines and the dotted lines, we get a very good representation of the data at various temperatures, ranging from 25 to 90 degrees C. And then in the next step, we will have an extended combination of MSC and CNT to model scaling inhibition, because the parameters of the nucleation theory can be related to the available concentration of the anti-scalants. And here is a preliminary calculation for the induction time as a function of the concentration of NTMP, one of the common scaling inhibitors. At 2 temperatures, we get the change, the increase in the induction time. So this is the idea. We are about to start this project, and we are really looking forward to bring the prediction of the induction time to a higher level, to a higher accuracy, so that our research partners and then our industrial clients can utilize it for modeling induction time in practical systems. So now I will turn it over to Vinit, who will talk about another project that we are about to undertake under the auspices of NAWI. Vinit.
Thank you, Andre. So this is the second initiative, which is more focused on integrating the OLI engine, which has the core numerical solvers, property database capabilities with the NAWI modeling and simulation software. So essentially what we are setting out to do here is to do a proof of concept to demonstrate mineral scaling prediction with the integration of the OLI engine with the NAWI modeling software. We do have a date here of March 31st set up as a milestone to demonstrate the initial proof of concept. And what this will involve is OLI licensing software to NAWI, providing technical support, and enabling the integration of the OLI cloud APIs with the NAWI modeling software, and also defining the actual application and use case, which in this case is going to be a seawater desalination use case to collaborate with the team. So this is something we're very excited about, looking forward to embark on also in the near future with the NAWI modeling and simulation team. So given the time pieces here, Andre, I'll just stop here. I think we'll see if we have any questions. We have a couple of minutes here, but I think that's pretty much it. You can go to the next slide, Andre. Okay, that's it. So
yeah,
we can open it up for any questions.
Yes, I can see that we have 12 questions in the chat, and some of them have been already answered. So I don't think we need to answer them again because the answers are already in the chat. And I think that the first question that has not been answered in the chat is, I believe, from Richard Breckenridge.
Yeah.
Great presentation. Thank you very much. With your predictive modeling and simulation, where do you think we are at or could be by merging your capability with your real-time sensors and controls or performance-based operating systems? Having AI autonomous systems would help mitigate operating failures or degradation by alerting operators before the event occurs during actual operating conditions. Yes, I really love this question because we are very much focusing on bringing the OLI technology to the operators. And the technology that we are using for this purpose is our cloud APIs. The cloud APIs are designed to work with the planned data, for example, through OSI soft platforms or possibly other platforms, so that we could the planned data can be fed into our predictive technologies, and then they can be brought to the operators using, for example, dashboards that can be designed, and ultimately this can be actually used exactly as you said, to alert operators before the event occurs. For example, we could predict, for example, the scaling tendency based on the concentrations that you can get from the measurements, or for example, you can predict pH excursions. We could predict also the corrosion propensity, because there's another functionality that we have in the software that we didn't talk about, and that is prediction of electrochemical corrosion. So we are definitely moving in that direction. Okay, the next one. What would you say are OLI software strengths, advantages over other available geochemical modeling software implementing the Pitzer and HKF models, such as EQ3, 6, PIC-C, Geochemist Workbench, Min3P, Tough React, etc.? Well, this is a topic for a very long review paper, but let me try to answer it briefly. The first advantage is that the model is really, the mixed solvent electrolyte model is applicable to very concentrated systems. So we have shown many times that we can handle systems going all the way to fused salts. So whenever you have really concentrated solutions, then the model has very strong advantages over especially the traditional molality-based Pitzer model. Of course, it can be argued that there is a mole fraction version of the Pitzer model which is available over a complete range of conditions, but in that case, also we have parameterized our model for a very large spectrum of systems. So in the database, you can really have the predictions over wide ranges of concentrations and temperatures out of the box. So the concentration ranges, the temperature ranges is one advantage. The database coverage is another important advantage. The third advantage is the availability of the framework, the thermodynamic framework, within software products. For example, ScaleChem, which speaks the language of production chemists, for example, speaks the language of people who analyze scaling, and that makes it much more productive for people and easy to use. The fourth advantage that I could mention here is that recently it has become available in the form of web APIs, which you can easily use to combine with anybody's software. And actually the web API vehicle will be used for our integration with the ProteusLib. Also, we didn't talk about it, but I would want to mention here the prediction of corrosion and also the prediction of transport properties. If you are interested in the prediction of, say, electrical conductivity or viscosity or diffusivity, or surface tension, then this is all integrated with the thermodynamic model, and this is not available through other frameworks, and it may be quite significant for some applications. For example, we can predict, say, electrical conductivity for very concentrated systems. So I think I have listed the most important differentiators. I may have forgotten about some, but I think that's how I would summarize it.
Well, thank you very much, Andre, Vineet, Kristen, AJ. We really appreciated your seminar today, and we look very much forward to hearing more about some of the advances as your NAWI projects move forward, as well as other developments that I'm sure you have in the pipeline. So we are slightly past the top of the hour. Appreciate everyone's participation and the active participation in the Q&A. And we will have more modeling and simulation presentations in the future. So stay tuned to look for announcements of upcoming opportunities to learn more. and to stay engaged with the work that's going on in NAWI. Thank you very much, everyone.
Thank you. Thank you very much.
Thank you very much.
Thank you.